Hey, ladies and gentlemen, hey, thank you for joining me on this February's webinar where we're going to talk about how to model switching systems perfectly. And this is a sneaky little webinar because I'm going to also show you how to do Monte Carlo simulation in Excel. Really simple. And actually, we're going to use the switching system to explain or to illustrate or teach you how to use Monte Carlo simulation, because that's the way to do it perfectly. Now, the term that you should see on the screen right now, the term independent. Now, why am I doing that? Well, switching systems are an example of scenarios which are not independent. For those people who've never heard of a switching system before, don't worry. We're going to make sure we go through and explain what a switching system is. But it's also a great example of how failures are not independent in many real world scenarios. And that means we are talking about failures which are what we call dependent. A switching system being a classic example of that. So what does a dependent failure mean? Well, let's illustrate what that could mean, or one way of illustrating with this really weird looking fault tree. So you can see this fault tree here, and for people who haven't heard of fault trees before, there's a lot of information out there which can teach you about what a fault tree is. When I say this is a weird fault tree, you might notice that right there, let's see if I can get my weather, right there, there's a weird looking shape, weird looking symbol. That's pretty good. That's what we call, oh, I went too far. Oh, no. My computer is now doing silly things. I'm sorry. That is what we call a priority AND gate or AND gate. And so an AND gate is a gate which has a round top and a flat bottom. So what's a priority AND gate? Well, an AND gate is often used to model what we call parallel systems, where where the system will still work if only one component is still working. So if you have a two-component system, components A and B, a parallel system requires component A and component B to fail for the system to fail. Now, a priority AND gate is an AND gate where the scenario is declared to be true, or the logic is declared to be valid, if you have two events occurring, event A and event B, but event A needs to occur before event B. And so this might sound like a really unrealistic scenario in the world of reliability engineering, but it's not. Oh, goodness. There we go. We actually have a lot of scenarios where the order in which things fail is very important. And in this fault tree too, we have another issue as well. We have the fact that these two components are the same. This is how we model a switching system in the real world. And again, if you haven't heard of a switching system, don't worry, we'll explain exactly what a switching system is. But you can see that for those people who are familiar with fault trees, this particular fault tree is a problem. We are not ever taught how to model or analyze a fault tree where we have multiple instances of the same component and we have this weird looking priority AND gate. So let's look what a switching system is to help us understand what dependent failure looks like. So here is a parallel system. And as I mentioned, a parallel system is the one we usually associate with redundancy. So in this case, we have two pumps on parallel pipelines, pump A at the top and pump B at the bottom. So this system will fail if pump A fails and pump B fails. But a switching system for these two pumps involves adding a third component. In this case, it's going to be a valve. Now you can see this valve is hooked up to the red light, or that warning light that is on top of the top pump. And there's a couple of wires connecting the two. And so why do we have this valve? Well, this pump down here is now what we call the standby pump. It can exist in a standby state. So if you have redundancy where it makes sense for the redundant component, the backup component, to be mothballed, to be looked after, to be kept in pristine conditions, while you want to isolate that component from ongoing usage and wear and tear. It's exactly what this valve, this switching valve, does for this switching system. So when the switching system is operating normally, the primary pump is doing all the work, the valve directing fluid flow through the top primary pump. Now, when there is an issue, we need to have some sort of sensing device say, hey, the primary pump has either failed or is starting to fail, which then sends a signal to the valve to then redirect fluid flow to the standby pump, the standby valve, the redundant pump, I should say. Now, the benefit of doing this is that standby pump has been protected for all this time, and that doesn't apply for a parallel system. If you have two pumps operating in parallel, well, from one perspective, both pumps are aging equally, regardless of the fact one will fail before the other. So switching systems can often drastically improve reliability performance, even though it's more complex and it adds a third component, that switching valve, which obviously can also fail in its own right. So to understand this in a little bit more detail, let's zoom in on some of these components. Now, the primary pump, as with any component or any system in the real world, it will have some sort of reliability function, which we'll represent with this function R subscript 1 of T. So that's the reliability function of the primary pump. The switching valve, it too will have some reliability performance characteristics. And remember, it only needs to last long enough to allow fluid to be switched after the primary pump fails. So the switching valve, when it switches, it too will have a reliability associated with this operation, with this event. So we'll label or describe that reliability with the function R subscript switch of T. So you can see things are getting a little bit complicated. We need our switching valve, which can still fail, to last longer than our primary pump. And the standby pump makes this system a little bit even more complex. It, by definition, has to have two reliability functions. The first reliability function is the reliability associated with it in its standby state. It means that this reliability function captures the probability that this standby pump will still be functional when the switching valve switches fluid to it after the primary pump fails. So this is going to ideally model much higher reliability, but still reflect the fact that a standby pump can conceivably fail in its standby state before it is asked to pump any fluid. But after it starts pumping fluid, then it's going to have another reliability function we'll characterize with the letters R subscript, or the symbols R subscript 2, which then models its time to failure after it starts being used in its intended way. So now we have, as a minimum, 4 reliability functions which capture and describe the nature of this switching system. So this looks like a bit of a mouthful, and it is. It can be a little bit challenging to try and get on top of how these things are going to fail. So let's introduce my patented random hands of failure to represent the different reliability characteristics of these 3 components as they are combined to create a switching system. So what are we going to see? Well, we know that for the primary pump, the random hand of failure associated with the blue tag, we might be able to do some sort of statistical modeling or analysis and characterize the time to failure of this primary pump with, let's just say, a bell curve. Let's just say this characterizes the time to failure of our primary pump. And we've done this through reliability analysis or modeling or what have you. And that means that we would expect 1,000 of these pumps to fail, their times to failure illustrated by these blue data points falling down. You can see that they are the times to failure are densest where the bell curve is the highest. So this represents the failure process of our primary pump. Now, for our switching valve, let's just say that its time to failure is characterized by this probability density curve. It's obviously not a bell curve anymore. It's not symmetrical. And it means that if we have these red data points representing the times to failure of 1,000 switching valves, they are distributed in accordance with the height of that probability density curve. So we have a different curve. And for those veterans of my webinars, you might recall that whenever you have a probability density curve of time to failure, which has a peak, then that by definition is describing components that wear out, those that accumulate damage. So let's go to our third component, our second pump. Now, it might be reasonable to expect that when this pump, which is often identical to the primary pump, when it's being used in its normal operating conditions, its time to failure might be described by this bell curve, which is the same as that for the primary pump. But when we look at the times to failure when it's being used normally, we need to understand that only is associated with operational conditions, because it is also intended to be mothballed, so to speak, in a standby state. So this second probability density curve, which in this example we'll say is another bell curve, is to the right, a little bit more spread out, but it reflects the fact that we expect on average our standby pump to last longer when it's being protected in the standby state when compared to the operational state. Now, in the real world, you would really hope that standby probability density curve is way to the right. You can see it only sort of maybe doubles on average the expected life of our standby pump when it's in the mothballed standby state. So in many real world scenarios, you would expect standby component to perhaps last 10 or more times longer when it's protected in the standby state when compared to operational state. But for the purpose of this example, that it's much easier to see curves which are a little bit closer together. And it also illustrates a really important concept. And so now we have a bunch of different probability density curves, four in particular, which describe how this switching system operates. And so we know how our switching system needs to work, in which case we have some rules. So let's just say we have a switching system and we are observing it being used in our factory, in our plant, on our vehicle, wherever the switching system is. So the very first thing that's going to happen, which causes something to change, is our primary pump failing. So let's just say this blue data point represents when our primary pump fails. Now, for our switching system to successfully switch to the standby pump, our switching valve needs to still be working when our primary pump fails. So let's just say we observe our switching system, and in this case, this red data point represents the time to failure of our switching valve. You can see we have a problem because our switching valve failed before our primary pump failed. That means that our system effectively fails when our primary pump stops working. So because our switching valve failed before our primary pump failed, we lose the benefit of having a standby pump. So that's one scenario which can cause failure in our switching system. Here is another scenario where we look at perhaps the same switching system after it's repaired or a different identical one. Now you can see that mercifully the primary pump has failed before the switching valve failed. And that means the switch system can switch. That's fantastic, but we're not out of the woods yet because now we need to see what our standby pump is doing while it's in standby state. And let's just say that this yellow data point represents the time to failure of our standby pump in a standby state. Well, unfortunately, unlikely as this might seem, it's still possible for things to fail in standby states. And because our standby pump had already failed by the time the primary pump had failed, there is no benefit to switching to it. So our system again, fails when our primary pump fails. So that's two scenarios which cause failure. Let's just say that on the third system we observed, or third attempt, we now have the primary pump time to failure represented by that blue data point on the left, but we can see the red and yellow data points are now to the right, which means the system can successfully switch. And we go to our standby pump and we observe how long our standby pump works in operational state. We have that orange data point falling down to represent that time. But here's the real benefit of switching systems. This horizontal axis represents time to failure, so time equals 0 on the left. So that duration there represents how long our standby pump works in its operational state. So we have to actually add that to the operational time of our primary pump, and our system will eventually fail when our standby pump fails. This is what switching systems are all about. As opposed to having essentially the stopwatch start at 0 at the same time for each pump, we want the standby pump to start working after the primary pump fails. And this can drastically improve the reliability of many systems in particular. And we often use pumps to illustrate switching system scenarios, and they're often the most common ones you'll see. But when you're able to switch to a standby redundant component which has been protected, that's when the time to failure of your overall system can be dramatically increased. And so hopefully that explains how our switching system works. And let's just say we observe a huge number of switching systems whose times to failure are represented by these different curves you can see here. Now we have if we plot these data points on a chart that represents percentage of things that have failed, look at what we get. We get a beautifully smooth curve with a couple of characteristics. What I mean by a couple of characteristics, what do we see in the middle? What do we see right there? Coming up right there. You can see we have a little hump. What does this hump represent? This hump represents when, as a rule, primary pump failure is causing the system to fail. And that means that for whatever reason, our system is not able to switch, and that little hump is caused, it results from our system not being able to switch and our primary pump causing that initial failure. Then we can see over here, this correlates with the scenario where our system has successfully switched. So we can see we've got some good things happening, really good things happening. And that's what you want your switching system to essentially do all the time. You want your primary component, when it fails, you want it to be replaced, or you want the standby component to take over. And that's why we have these wonderful reliability improvements associated with standby or switching systems. Okay. Well, sorry, that's got ahead of myself. Successfully switched. And then our system eventually failed and we have standby system failure. Now let's compare this to our parallel system of these same pumps. If we have these same pumps used but configured in a parallel system or a parallel configuration, what do we see? We see that we have a very different reliability curve. It is obviously, this is a failure curve, I should say. We can see that it is now much higher than what appears to be the failure probability curve of our switching system. And just try and take a mental snapshot of this look. You can see that there is a huge difference between our failure probability of our parallel system and that of our switching system. The only time our switching system has a higher failure probability is right down there, where we have premature switching valve or standby pump failure. And this is, you can see that now we have, as a rule, a much higher reliable switching system. But as a rule, if we have a very reliable switching valve, our failure probability curve for our switching system is much better. This is what it looks like when our standby pump hardly ever fails in standby states, along with our standby component. And so the idea is that we want to maximize the overall use. Oh, I'm very out of focus. Excuse me while I fix that. You want to maximize the overall use. Oh, you can see my face, so that's zoomed in. No one wants to see that. But you can maximize the overall useful life of your product, of your components, by essentially allowing them to add up in terms of creating overall system time to failure. Now, the way we get these curves is really fun. And when I say really fun, here is the equation that gives you the reliability of your switching system based on all those characteristics, all those reliability curves we looked at. This is a terrible equation to solve. There's no analytical solution. For those people who think this is awful, don't worry, it is. And you need a computer to numerically solve this for you. But just to go through this equation in a little bit more detail, we have these two functions up the top, R subscript 1 and F subscript 1. These are all about the reliability characteristics of the primary pump. Here we have the reliability characteristics of the switching valve. And we also have the reliability characteristics of the standby pump in standby state. And at the bottom, we have the reliability characteristics of the standby pump in operational state. And so we have this awful equation, which is used to model the switching system reliability. So to do that, in many cases, lots of engineers make horrible assumptions. One of the first assumptions they make is that the switch is perfect. It never fails. And so its reliability is 1 or 100%. So we can essentially remove that from this horrible equation. The second assumption that is made is that the standby pump never fails in a standby state. So it's in a perfect standby state. So its reliability in the standby state is 1 or 100% all the time. So we can remove that from our equation. And the third and most awful assumption that many engineers then make is that both pumps have the same constant hazard rate. And the reason they do that is because the reliability equation for such a scenario is really simple, and it's based on this variable here, which is called Euler's number. There's the constant hazard rate for both pumps, and we know that pumps wear out. They have increasing hazard rates, but having a constant lambda in this case implies they never wear out, they never get old, they never start young. And so once we have these equations, we can put them into this terrible equation here, but it allows us to do a little bit of interesting math to then break this equation down into this one here. And this becomes the reliability equation for such a perfect switching system where both pumps have the same constant hazard rate. And this allows people to come up with reliability numbers without having to use a computer. But there is a cost for that. So let's go back to the failure probability or the failure function or failure curve for our switching system, which we just identified. Now if we were to identify the mean time to failure of each pump and then identify a constant hazard rate for each one and feed that constant hazard rate into the equation we just developed for that perfect constant hazard rate switching system where nothing fails before.
Lean's article by accident. Is there a way to see?
Sorry, is someone asking a question?
Yeah, there is.
Sorry, what was that? Someone asking a question?
Oh, sorry.
We're good? Okay, my apologies. So here is the failure curve for our switching system. Now, if we put those assumptions into that perfect constant hazard rate switching system, this is the failure curve we get. Now, as you can see, it doesn't really marry up with the actual failure probability at all. In fact, you'll drastically overstate the failure probability when your switching system is young, which is usually the time where we care the most about reliability performance for things like warranty and the rest. And it will drastically understate the end-of-life reliability performance. It will say, or failure probability, I should say. And so hopefully you can see the pitfalls of trying to simplify what appears to be a relatively complex system with these horrible assumptions just to get a number, because that number is heinously wrong. And for a switching system, what's the point of having all this wonderful additional functionality to extend the reliability of the system if you're going to use an equation which says the reliability is still terrible? We don't want to do that. So we want to never use the perfect switching system with constant hazard rate model. It's just terrible. So how do we find this green line based on that horrible equation we just went through? Well, the answer is through Monte Carlo simulation. Now, Monte Carlo simulation is often an intimidating phrase. People hear it and then run for the hills. That sounds like something that only university students do. In this webinar, I'm just going to give you a very high-level example of how you or anybody else can do this in Excel to a high degree of accuracy. And it's really, really simple. So one of the first things we need to do when it comes to Monte Carlo simulation is understand what it is. So if we go back to our 3 random hands of failure, and which represent the different way things fail in our switching system, we then take those random hands of failure, embed them within this Monte Carlo simulation concept, and get amazing results. So where does the concept of Monte Carlo simulation come from? Well, Monte Carlo, it refers to the casino, the Monte Carlo casino in Europe. It's a code name. The reason why it's a code name is because it's such a powerful tool that when it was first dreamed up by the gentleman's name escapes me, but when it was dreamed up by one of the scientists in the Manhattan Project, its value was seen as so high, so useful, where they were going to use this approach to model really complex concepts. They had to give it a name. And so this gentleman recalled his uncle, who liked to play solitaire at the Monte Carlo casino, and the Monte Carlo code name was used, and it's stuck ever since. And the reason why the Monte Carlo casino is referenced is because Monte Carlo simulation is all about simulating chance occurrences, like dice rolling, for example. It's really straightforward, and Excel can simulate these random processes very, very easily if you know the characteristics of those bell curves, the Weibull distributions, the log normal distributions, or whatever distribution you have that characterizes the time to failure of components in something like a switching system. So for Monte Carlo simulation, there are 5 steps. The very first step for Monte Carlo simulation is to model system failure based on component failure. Then we model how components fail with probability distributions. We then simulate times to failure for each component. We then simulate system times to failure, and then we generate reliability information. And it's so straightforward, you can do this in Excel. Now, when it comes to intimidation, don't worry, those steps might sound problematic, but they are really straightforward. And I'll take you through some of those steps right now, going back to step number 1. We model system failure based on component failure using logical rules. What does that mean for our switching system? Well, if we take step 1 to our switching system, we're trying to model system failure based on component failure using logical rules. We know there is one rule that applies to scenarios where the system time to failure is given by how long the primary pump lasts. The system time to failure is equal to the primary pump time to failure if the standby pump in standby state or the switching valve time to failure is less than the primary pump time to failure. That means if your standby pump or your switching valve fails before your primary pump fails, then your system fails and the primary pump fails. So that's rule number 1. Rule number 2 is that if your system hasn't failed due to rule number 1, then your system time to failure is equal to the primary pump time to failure plus the standby pump time to failure in the operational state. And these are the only two rules you need. This characterizes, describes how your switching system fails. So just two rules. So that's step one. So hopefully you're with me so far. And if you don't have switching systems, but can see how this is applicable to your scenario or your workplace or your profession, then all you need to do is work out what rules apply to how your things fail in order. Step number one is done. Step number two is we model how components fail with probability distributions. We've already sort of touched on this because we actually do this for our random hands of failure. So all our random hand of failure is doing exactly what step two asks us to do in Monte Carlo simulation. So let's say that we have done the reliability analysis and determined that our primary pump fails, time to failure is distributed in accordance with this bell curve here. And we know that means that if we observe lots of primary pumps failing, their times to failure will be distributed in accordance with the height of this bell curve, which is also known as the normal distribution. The mean of this bell curve or normal distribution is the balance point underneath that probability density curve, of the area beneath that probability density curve, and the standard deviation describes how spread out that probability density curve is. So let's just say after analysis, we found that the mean time to failure for this pump was 1.0 and the standard deviation of times to failure was 0.2 for argument's sake. And I'll keep these numbers unitless to try and reflect the fact this is applicable to any scenario. So now we've characterized the time to failure for the primary pump. Now for the switching valve, let's say we've done some analysis and I found out that the time to failure for our switching valve is modeled by a Weibull distribution, which is described by a shape parameter beta and a scale parameter eta. And there's lots of other webinars I've done out there which teach you about the Weibull distribution, which is a great way of modeling things where essentially the strength of the weakest part of your component is modeled or drives failure. And so in this case, let's just say we've done some analysis and identified that this switching valve has a shape parameter of 1.5 and a scale parameter of 1.4. So that's the switching valve. Now, it's the standby pump's turn. It has two probability density curves. Remember, the operational time to failure for the standby pump is the same as that for the primary pump, so it has a normal distribution with the same parameters. And then in the standby state, we have this bell curve normal distribution to the right. So it has obviously a higher mean and it's a bit more spread out. So the standard deviation is now 0.32 instead of 0.2. So there we have, essentially, we have characterized all the different ways our components fail or our switching system. So what do we now do with this? Well, that's essentially step two completed for our five-step Monte Carlo process. We have these four probability density curves characterized. Step number three means that we start simulating component times to failure. And that's why we did step two, because we need to come up with those parameters to simulate those times to failure. And so if we go back to our random hand of failure, all we are doing in practice is asking our random hand of failure to generate these, in this case, I think 10,000 data points. Now that might sound really straightforward, really complex, I should say, but Excel can really help us do that. So if we replot this data in a chart where it characterizes the percentage of things that have not failed, it's a beautiful, smooth reliability curve. Now, reliability is obviously the probability that an item is still working at a particular point in time. But to simulate these times to failure, all we need to do is get a number of equally spaced points on this vertical axis. We draw them across to our reliability curve, and look what happens. See all those blue dots? Look what happens when I draw lines down from those blue dots. And you can see all those X's that are marked along the horizontal axis. And when I put that bell curve back, you can see that those X's are now distributed in a way that's described by that bell curve. And so this is how computers can simulate random variables. If you tell them what the bell curve is, you can generate a reliability curve from that bell curve, which allows a computer to put uniformly spaced simulate uniformly spaced reliability values. You draw lines across and the lines go down, and now we've simulated times to failure for our primary pump. The problem with this is that if you want to have equidistant reliability numbers, you need to start with a certain number. Might have to be 20, 10, because you need to know how far spread out they are. And sometimes we don't want to have a number. We want to keep going until we reach a level of accuracy. Well, so an alternate is just to randomly simulate up and down that vertical axis. And so in Excel, we can use what's called the inverse reliability function that takes that reliability function, and instead of finding the reliability at a particular point in time, you start with the reliability in question. It then essentially draws a line across, allowing you to create those or simulate those times to failure. So the inverse reliability function simulates times to failure. And again, this might sound intimidating, but we're going to go through this in a really straightforward way.
I'll start.
Oh. So before we move on, we're going to go to a pre-recorded video of me doing this in Excel. So hopefully my pre-recorded video is going to, with the audio is going to come through and you'll be able to see exactly what I'm doing.
I'll start with column A for the simulation number. I'll enter index into cell A1 and the formula equals sum with A1 in brackets plus 1 in cell A2 to set up this row for the first simulation. I'll select B2 and go to the view menu and select freeze panes so we always see the first row and column. Now I'll use column B for randomly simulated reliabilities of the primary pump. In cell B2, I'll enter this formula where the letters R, A, N, D are short for random. When I hit enter, I get a randomly simulated number between 0 and 1. If I press the F9 key, Excel generates a new random number. Anytime you modify any cell or press F9, Excel recalculates everything. I'm going to format this cell as a percentage. Cool. We now have a randomly simulated reliability percentage. I'll use column C for the simulated primary pump time to failure, which we know is described by a normal distribution with a mean of 1 and standard deviation of 0.2. In cell C2, I enter this formula where NORM is short for normal distribution and INV is short for inverse. You can see the mean and standard deviation represented by arguments 1 and 0.2. The B2 argument references the randomly simulated reliability value from cell B2. And when I press enter, we get a simulated primary pump time to failure in cell C2. I'll do this for the other components, starting with column D for the randomly simulated reliability of the switching valve. You must randomly simulate a new reliability for each component. If you don't, Excel will simulate the same type of failure for all components, be they early failures, late failures, or somewhere in between. I'll use column E for switching valve time to failure, which is modeled by the Weibull distribution with a shape parameter of 1.5 and a scale parameter of 1.4. Excel doesn't have an inverse Weibull reliability function, so I need to write it. So I'll select cell E2 and enter the inverse Weibull reliability function and its parameter values manually. Let's use column F for standby pump randomly simulated reliability in standby mode. And column G for the standby pump time to failure in standby mode. Remember that this makes our pump last longer before it's used. With standby mode time to failure modeled by a normal distribution with a larger mean of 1.5 and a standard deviation of 0.32. So I'll enter the inverse normal reliability function here to simulate the standby pump's time to failure in standby mode. Let's repeat this process for randomly simulated reliability of the standby pump in operational mode in column H. And its simulated times to failure in column I, which are described by the normal distribution with a mean of 1 and standard deviation of 0.2. This is the same as the primary pump, so all I need to do is select and copy cell C2 and paste it in cell I2. Even though they share the same normal distribution, you can see their simulated times to failure are different as each is simulated independently.
All right, so that was a lot, but don't worry, it's in your guidebook. And if you can follow that conceptually, I don't expect you to remember all the equations, it's in the guidebook. But now, at this stage, we've been able to simulate the times to failure of 4 components, or at least 3 components, with the standby pump having 2 different modes of failure. So step number 4 means that is then our simulating system times to failure based on our component times to failure. And so what that means is that, remember those rules? We need to take these 4 times to failure and learn, work out what that means at our system level. Remember, rule number 1 was that our system time to failure equals our primary pump time to failure if both the standby pump in standby mode and switching valve fail before our primary pump fails. That's the first rule. Second rule is, come back, is our well, it's not coming back, unfortunately, is that our system time to failure is equal to primary pump time to failure plus standby pump time to failure if rule 1 doesn't apply. So let's go back to Excel and see what we can see.
I'll use column J for switching system time to failure. And in cell J2, I'll enter this equation that represents our 2 rules with simulated times to failure in cells C2, E2, G2, and I2. The OR term tells Excel when to switch between the 2 rules and use either the primary pump's time to failure or the sum of both pumps' time to failure. And when I press enter, magic. Here's a simulated time to failure for our switching system based on its components and failure rules with no horrible equations required. But one simulation isn't helpful. We need to simulate lots. So in the top left corner of our spreadsheet, we're going to enter A10001 into what we call the cell address box. And Excel then takes us straight down to cell A10001. Then I'll press Shift and the right arrow several times until I reach cell J10001. I press Control or Command Shift and the up arrow to select all cells between A2 and J10001. And finally, I press Control or Command D to populate all these cells with simulated times to failure.
Right, so again, it's a bit of a speedy one. I know we've only got an hour's worth of webinar here, but all those equations are also in the guidebook. But what we've done now is, based on our understanding of the logic of failure and the probability distributions of the times to failure for our 3 components, we have 10,000 randomly simulated switching system times to failure. And that means we're almost done. We've just finished step 4 or 5. And step number 5 is to generate reliability information, because those having 10,000 numbers is great, but let's see what that means in terms of actually extracting useful information. And to do that, we'll go back into Excel.
One thing we can do is create a reliability chart. I'll label column K sorted switching system times to failure and use Excel's small formula in cell K2 to get the shortest switching system time to failure. In cell L1, I'll enter switching system reliability followed by this formula in cell L2 and format it as a percentage. This estimates reliability at the shortest simulated switching system time to failure. Now I'll enter K 10001 in the cell address box, shift right arrow, control or command shift up, and control or command D. Now we have 10,000 ranked switching system simulated times to failure in column K and their reliability estimates in column L. We can see this data better with a scatter plot. I'll select cell K2, press control or command shift down arrow and shift right arrow to select the system times to failure and their reliability estimates. I'll use the insert menu and select scatter plot using the top smooth curve. At the top of our spreadsheet, we have a chart which I'll tidy up like this. This is now a reliability curve that can help you answer questions about warranty, L10 lives, and lots of other things.
So there was our right here is our switching system reliability curve from those 10,000 data points. And you can see it's relatively smooth. Now, if you want to improve the accuracy, notwithstanding this is pretty accurate, you can, instead of simulating 10,000, simulate 100,000 or a large number. Now, when it comes to understanding how many samples you need, that's not a straightforward question to answer. For example, if you're going to use a curve like this to try and estimate what time reliability is 99.9999, well, you need a lot more simulations because you're only examining just the tail end of this reliability curve, and that's where the highest inaccuracies are. You might need, in some cases, millions of samples to get that, and that's beyond the capability of Excel. If you're trying to understand the L10 life, the time by which you expect 10% of your switching systems to fail, then maybe 10,000 is a really good, is a good enough number for you. And of course, if you're trying to answer a question like, does reliability exceed a certain value at a certain point in time? Well, if this curve shows that your projected reliability performance is really, really high compared to the reliability requirement, then you don't, even if it might not be perfectly accurate, the fact it is so much higher than your performance target, you don't need a ton of simulations. 10,000 might be all you need. If the performance requirement and the reliability curve is very close, you might want to then have some more simulations to make sure that the perceived reliability performance is not just exceeding the requirements because of inaccuracies. So there's no right or wrong answer for there is plenty of wrong answers, I should say, for how many simulations you need, but all you need to do is increase the number. And I often do Monte Carlo simulation in MATLAB, which can handle huge numbers of simulations really easily, way more easily than Excel. But I love using Excel to talk about Monte Carlo simulation because everyone knows how to use Excel. And Excel is perfectly good at doing Monte Carlo simulation. If you, for example, you only need 10,000 or maybe even 100,000 simulations to answer a question. And in many cases, that is all you need. 100,000 simulations is often more than enough for many reliability decisions. Sometimes it's not, but if you're going to start to learn how to use Monte Carlo simulation to model really complex systems like switching systems, then Excel is a great place or great software medium to practice the art. And in this case, you can see that curve, those humps we were talking about, where we have the initial decrease because we have our primary pump failing before our switching system. After our switching system or standby pump has failed, and we have that second hump where the switch successfully occurred and our system now fails after our primary and standby pumps have failed. Now, this curve is quite unusual. You would usually have a switching valve which is highly reliable, so you essentially not see that hump. Maybe you do. Maybe your switching system or switching valve in your scenario isn't very reliable, or maybe you're not using pumps at all. Maybe you're using something else which has limitations, technological limitations on the ability to switch, and so there might always be that hump. But the only way to find out is to use this sort of approach. Hopefully, one of the takeaways is the equation we often see in textbooks for that perfect switching system. perfect switching system, which doesn't have, which has constant hazard rates, which is an assumption which is terrible and it's wrong. That will give you numbers which make no sense. That will overstate failure probability, understate reliability, and you might have designed a wonderful switching system which now meets requirements, but when you use those outdated equations, the number says you need to keep working, and that's just wasted effort for a system that's already reliable enough. In many cases, the so-called perfect switching system equation actually creates worse failure probabilities than a simple parallel system, which is just not possible. So hopefully you got something out of this webinar. Hopefully you're not as intimidated by Monte Carlo simulation, if indeed you ever were. And I'll open up the floor to questions. Noting that, what do we have here? See that Carl writes, think reliability uses Microsoft Excel for root cause analysis, RCA, by leveraging its drawing tools, shapes, structural capabilities to create cause maps. Key tips include control plus drag to quickly duplicate boxes, utilizing the control plus T shortcut to turn data into tables, and utilizing the cause mapping template to document investigations. Fantastic. That's for RCA, but I wouldn't say that is super applicable to Monte Carlo simulation of the conversation today. Are there any questions? Anything else that people want to ask? I believe the question was asked halfway through verbally. Are we wrong? I'll head back in the focus zone. Any questions? Thank you. Thank you, Nazri. You're welcome. You could apply to a manual switching system where you have to consider human reaction time, human error probability. Absolutely, you could. And that's where Monte Carlo simulation becomes really, really helpful. For example, you just simply need to modify your rules so that you have you incorporate the human reaction time to your system time to failure, or perhaps the human reaction time is also counts as downtime. So then you have to modify what it is you're looking at as opposed to reliability. It becomes availability. But all you do is replicate those columns that I had in that example spreadsheet. It's really simple. Once you become comfortable with some basic examples like this, you'd be amazed at how much sophistication you can really embed into your models. And yeah, human reaction times are a big one for those sorts of situations. Thank you, Michael. Just a question. I often, Fred doesn't like my webinar titling skills with some justification. So I often don't simplify what the main point is. I suspect there's a chance, and I'll ask for feedback on this point. Would a webinar titled Monte Carlo Simulation be something you guys would have otherwise been interested in? And perhaps if this was couched as an example of Monte Carlo simulation, would have been more useful to help you decide whether to turn up today? Thanks, Chris. Okay, Carl asks and answers his own question about model-based systems engineering. So the question I'm asking you guys, if anyone's brave enough to venture an opinion, would a webinar focusing on Monte Carlo or titled Monte Carlo simulation be perhaps a more appropriate one for this one? I'm not going to go into MBSE today, Carl. It's a useful concept, but it is it's not an example of Monte Carlo simulation. Okay, thanks, John. There we go. All right, so if I'd had Monte Carlo simulation, I would have driven people away. Thanks, mate. Okay, what is a document that would have all those parameters that represent the characteristics of those components? FMEA? No, FMEA would not. A FMEA is a great tool. I'm not trying to downplay it. It's a great tool at identifying early in design what the weak points are. Often FMEAs are seen as a catch-all for every single failure scenario. And often you'll have FMEAs, which have hazard rates or failure rates associated with each failure scenario, which are essentially useless most of the time because they're simply parts count predictions or Google values and not based on analysis of your system. That said, for me, it'll be very helpful for you identifying what the 5 dominant failure mechanisms are or of a scenario to help you characterize its reliability. Now, for a scenario like a pump, which you get from a third-party supplier, you would have to interrogate their data, their performance data, if they're willing to share it. Many companies are. Some of those companies that share data, the data is not representative. It sort of overstates reliability performance. But if you can, that'd be fantastic. And that, so if you can't, then you often have to do your own testing and or analysis. So for pumps, accelerated life testing is one way of doing that. Switching valves, not quite as straightforward because the failure mechanisms involved are largely associated with the accumulation of stuff, which essentially makes bearings and things seize. And so that can be a little bit challenging to identify. But as a rule, you could you would hope the reliability of your switch is somewhat larger than that of your pumps. Now, to that end, what you can do is make some conservative estimates of component reliability. And if those conservative estimates of component reliability, the means and the standard deviations, still mean you exceed your performance, then that's a good assurance activity, even though you're understudying your switching system reliability. Or depending on what decision you're trying to inform. Are we meeting requirements, yes or no? Understating or making pessimistic assumptions on those parameters, doing the analysis, and if it still exceeds requirements, you're good to go. So there's no straightforward answer to that particular question, but hopefully I've given you some pointers. Modeling of switching systems with artificial neural networks, any thoughts? Yes, I don't see any reason to do that. I think that we are being neural networks and machine learning principles more broadly, they are often a siren call for reliability engineers or engineers who think they're reliability engineers. But the reality is that's such a sophisticated technique that you really should have done the bare basics from the very start. The analogy I use is Cristiano Ronaldo. So Cristiano Ronaldo is perhaps one of the most comprehensively gifted athletes the world has ever seen. One of the things he does is he has his own hyperbaric chamber in his house, which I think he spends most evenings in that chamber. So why am I using that as an example? If you wanted to become as fit, as healthy, or maybe as a good a football player as Cristiano Ronaldo is, and you decide to install a hyperbaric chamber in your house as your first step, do you think that's really going to make a difference? The answer is no, and that's because Cristiano Ronaldo, from a young age, his dieting is spot on, his exercise regime is spot on, he practices it just as hard as anybody else. And so for someone who is as much at the top of the game as he is, he then needs those hyperbaric chambers and those very high level things to polish off what is already a really impressive skill set. But if anybody else was to start their soccer journey or football journey with a hyperbaric chamber, they would get absolutely no results. That's what I'd argue that's how I'd argue neural networks, how neural networks applies to reliability engineering. I'd see too many people want to go straight to neural networks as opposed to doing some really simple reliability stuff at the lowest level to improve reliability. And then you sort of wish away your reliability problems with this mythical, all-seeing, all-knowing neural network, which is supposed to give answers for everything. And I'm not trying to suggest that neural networks aren't powerful. They are. But you need to do the basics first, the same way Cristiano Ronaldo does his basics first as well. So hopefully that answers that question. Model checking methods for mode switching systems. I'm not sure what a mode switching system is. So I'm not sure how to answer that one. Yeah, I'm not going to go to that PDF right now, Carl. Which is a thesis, a PhD thesis, no less. I have about less than 60 seconds in our allocated time. So that would be an ambitious undertaking to try and peruse that, summarize that, and use it to answer your question. Any more Q&A? Or any more Q, and I'll do the A. All right, team, thank you for your time. Notwithstanding the discussion about the title, I may sort of rebadge this webinar and retitle it as Monte Carlo Simulation webinar in the future, or might use it to generate a Monte Carlo webinar in the future, because there might be a number of people who didn't turn up today who would have if they saw what it was all about. Thank you, Alexander. Yep, not going to look at that link either, Carl. Running out of time badly. All right, thank you, Marcel. Did I answer your question, Marcel? You're welcome, Sky. No worries. Honest. Like it. One thing I would say, Marcel, is just don't assume. Markov switching models in economics, any thoughts? Possibly, but yeah, I think we're running out of time, Carl. And Markov, again, with Markov chains, unfortunately, they're sort of focused on constant hazard rate assumptions. Thanks for turning up today, and I'll see you in my next webinar, where it's all about maintenance. And for those where I actually broach the concept of perhaps there are scenarios out there where every failure is caused by maintenance. That's an astounding claim, and I might be able to prove it to at least some of you for some situations. If that's interesting to you, I'll see you next week, the next month, I should say.